so you guys remember the Schrodinger equation? That was a really nasty one that he put up on the board, like when we had the sub. And he's like, look at this equation. And you all started writing it down and like highlighting it in cool colors and stuff. And then he's like, you'll never use it. So that's the Schrodinger equation. Okay, when we solve the Schrodinger equation, what do we get? What's our answer? Psi. Okay, it's that trident thing without the squared. Okay, psi. What is another name for psi? Wave function. Okay, that it has to do with the energy states that your electrons can have. Okay, but do we use psi for anything? No. What do? We square it, and when we square it, what do we get? Somebody raise their hand. Almost. Is there a hand? What's up? Yeah, we get a probability density. Essentially, we get, you guys remember this picture? It looked like this, and it had like a million dots on it. Yeah? Okay, it's showing where the electron could be at any given time. Okay, so what do we do from that to get an orbital? Okay, we put a boundary around 90% of those dots. And then we call that the orbital. Okay? Is that fair? Does that make sense? Am I lying to you? You wouldn't know. So, okay. That's how we get an orbital. What is a node? Somebody raise their hand. In terms of orbitals. Rob here.
Probability of finding an electron is 0.
Perfect. Where the probability of finding an electron is 0. Electrons cannot exist on nodes. All right. What else? Uncertainty principle. Heisenberg uncertainty principle. Anybody? Yeah.
The more you know about velocity, the less you know about the position of an electron.
So that was awesome. That was perfectly stated. What he said was, the more you know about the velocity of electron, the less you know about where it is. Okay, there's some uncertainty that's just inherent in these super, super small things, okay, that I can't know both. Okay, so if I really know, if I have a good idea of where it is, I have a bad idea of how fast it's moving. If I have a good idea of how fast it's moving, I have a bad idea of where it is. Okay, that's the Heisenberg uncertainty principle. You had like, there's that one equation that none of you knew how to use because we didn't learn how to use it. I'm guessing you won't have to worry about it. Okay. Oh, think about it again. Okay, ready, go, done. All right. What? That's psi. That's the solution to the Schrodinger's equation. It's called a wave function. But then we square it to get that. Just a conceptual, like I just said. Density, probability. Okay. Okay, moving on. We're getting to quantum numbers, guys. This is where it really gets cool, right? Actually, you can talk to each other while I erase the boards. Okie dokie. All right, let's bring it back. Okay, let's talk about these. Let's talk about these quantum numbers, okay? If you're a nerd, what do you call the first quantum number? N. Yeah, okay. If you're a normal person, what do you call it? N, yes, okay. Shell or energy level. Okay, what are the possible values for N? No. Okay, 1, 2, 3, 4. Positive integers, right? They're the same N's that we've been dealing with this guy. Okay? All right. Awesome. What is L if you're a nerd? Angular momentum quantum number. But otherwise we call it subshell. And we'll also refer to it as like the shape of an orbital or the type of an orbital. Okay, what are the possible values? Wow, I didn't leave myself much space. What are the possible values for L? Okay, everybody always says n minus 1. It's 0 up to n minus 1. Okay? 0 up to n minus 1. So If n is 1, what's L? 0. If it's 2, we could have both 0 and 1. Okay? If it's 3, 0, 1, 2. If it's 4, 0, 1, 2, 3. You following? Okay, cool. What do these numbers mean? Because they don't mean they're numbers. Well, I guess what do they mean? They tell you the shape. And how do they determine the shape? The nodes. This is the number of planar nodes. This is the number of planar nodes. How do we find total nodes? N minus 1. Okay, but this is the number of planar nodes. So if I have 0 planar nodes, what does my orbital look like? It's a sphere. We call that S, right? What if it has 1 planar node? P, 2, D, 3, F. Okay? So far, so good? Okay, what do we call M sub L? What's the nerdy name? Magnetic quantum number. What's the useful name? Orbital or orientation or orbital orientation. Okay? This is telling us now of this type of orbital, how many do we have of that type, right? What are the possible values? Negative L up to positive L. So if it's 0, I got 0, 0, negative 1, 0, 1, 0. Oh. Cool. So, do these numbers themselves mean anything? No. What matters? How many numbers there are. Okay, what this tells me is if I have a p orbital, the L is 1, so my M sub L is negative 1, 0, 1. So how many p orbitals are there? 3. Because there's 3 numbers. How many d orbitals are there in any level? 5, right? Because for d, L is 2, and negative 2, negative 1, 0, 1, 2. Okay? How many total orbitals exist in n equals 3? How many total orbitals exist in n equals 3? Who has no idea where we got 9? That was like where all the Hansen students, just kidding. That was a joke. It wasn't even where the Hansen students were sitting. Okay. So if I just look at n equals 3, if I draw this out and just count, 1, 2, 3, 4, 5, 6, 7, 8, 9 orbitals. One of them is an S, 3 of them are P's, 5 of them are D's. Okay? Or you can just square n. Okay? That doesn't mean anything, that's just how it happened. Okay, it's just how it works out. Okay, how many, okay, we're good. How many electrons then can fit in n equals 3? 18, right? Because if we have 3, then we have 9 orbitals, and each orbital can have 2 electrons. So that leads us to m sub s, which is what? Electron spin. And for every orbital, it has those 2 values, plus 1/2, negative 1/2. Cool? Okay, so then now, let's describe some differences between orbitals and orbits. Okay, I can think of 3. No, I just know that I'm supposed to be able to think of 3. I actually can't think of them right now. But there are 3 big differences, okay? Who's got them? Who's got one difference between an orbital and an orbit? You guys know what an orbit is? These things are orbits. These Bohr model circles. Go ahead. Orbitals are 3-dimensional. Orbits are 2-dimensional. Awesome. Yeah.
Orbitals are chaotic. They don't follow a pattern.
Okay, so a better way to say that is an orbit, because they do follow a pattern, right? We know what a p orbital looks like. But an orbit says this is where the electron is. An orbital says this is where it's probably 90% of the time. Does that make sense? Okay, and then what's one last difference? Has to do with how it treats an electron's nature. Okay, a Bohr model treats electrons as particles, whereas orbitals treat it as a wave, standing wave. Okay? So those are the 3 big differences. Good to know, because it's on the study guide. All right, so go ahead. What time are we gotten? We're good, we're good, we're good. Okay, I want you to talk together, identify this orbital. Yeah, so,
Like orbits is where the electron is, and orbitals are more like where they place it.
okay, and then orbits are two-dimensional, or 2D, and orbitals are 3D. And then lastly, I said, orbitals treat electrons as waves, orbits treat them as particles.
So waves and then particles.
Yep.
Thank you.
Yeah. Alrighty, let's bring it back. So, for this, I got 4p. And for this, I got 5d. Okay, so let's talk about how we figured this out. How many planar nodes are here? 1. So that means L is 1, which means I have a p orbital.